Hello everyone. Having learned the experimental gas laws in the previous lectures, now we are in a position to develop a theory to explain these experimental gas laws. And fortunately, we have been able to develop a theory, and this theory is based on the shape or the structure of gaseous molecules, and this theory is known as kinetic theory of gas. Now this kinetic theory of gas is based on certain postulates, and which is these postulates are the backbone of this kinetic theory of gas, and these postulates are applicable only to the ideal gas that we have defined in the previous lectures. The concept of ideal gas, what is ideal gas, and which type of gas will follow which type of equation, that is what we call as equation of state and ideal gas. Now coming to the heading, that is kinetic theory of gas. So we have kinetic theory of gas, KTG. As I told you, this kinetic theory of gas is based on the certain postulates. So let's look at these postulates. Postulates of this KTG, kinetic theory of gas. First postulate. Now we are having a sample of gas. In this sample of gas, that consists of a large number of tiny spherical particles. These tiny spherical particles are considered, these are the molecules. That means the molecules of gas are considered to be tiny spherical particles. So all gas molecules are considered to be spherical particles. So the gas molecules, tiny spherical particles. So means all gas molecules are considered to be tiny spherical particles, and in a sample of gas, all molecules of a particular gas are identical in shape, size and nature. Molecules of a gas are identical in shape, size and mass. That means all the molecules of a particular gas are considered to be tiny spherical particles, and all these tiny spherical particles, which is considered to be the molecules, are identical in shape, size and mass. Second postulate of this kinetic theory of gas. Now the volume occupied by the molecules of gas in comparison to the total volume of gas is very negligible, or considered to be approximately zero. That means we have a sample of gas which has total volume. So in comparison to the total volume of the gas, the volume of each and every individual molecules is approximately zero. That is very negligible. Volume occupied by the molecules of gas volume occupied by the molecules of gas in comparison to the volume of gas is approximately 0. So look at this, I am giving this a star mark. So volume occupied by individual molecules of the gas in comparison to the total volume of gas is approximately 0 or very negligible. Third postulate, now these gas molecules, whenever these gas molecules move, they always move in straight line in random chaotic motion. That means they always crisscross each other, but whenever they always move in straight line. Motion of gas molecules is random or chaotic motion, and they always move in straight line. So whenever they move, they always move in straight line, and this motion of gas is always crisscross, that is always random or chaotic motion. Number 4 postulate. So we are having gas molecules, they are moving in straight line and random motion. So whenever gas molecule moves, in between the gas molecules there is no force of attraction or repulsion. No force of attraction or repulsion exists between the gas molecules. Force of attraction or repulsion between gas molecules, that is, no force of attraction or repulsion exists between the gas molecules. That means whenever gas molecules are moving in a particular direction in a random motion straight line, the motion of each and every individual particle is independent of the neighboring particles. So the neighboring particles will not have any influence on the motion of any particular individual gas. So whenever gas moves, they are independent, and that is totally free from neighboring atoms. This is the meaning of no force of attraction or repulsion between the gas molecules. Again, I am giving a star mark. Number 5 postulates for this kinetic theory of gas. Now we are having these gas molecules, they are moving in straight line, and the motion is independent of the neighboring molecules, and whenever these gas molecules moves, the effect of gravity on the motion of gas molecule is negligible. So I repeat again, the effect of gravity on the motion of gas molecules is negligible. Effect of gravity on the motion of gas molecules is negligible. Number 6. Now again look at this. These gas molecules are moving in a random motion, in a chaotic motion, in a straight line, independent of the other molecules, in which the effect of gravity is negligible. Now these molecules, whenever these molecules moves, they always occurs in infinite numbers of collision between the gas molecules. So whenever these gas molecules move, obviously there is chances for collision between the gas molecules. This collision between the gas molecules is not responsible for the pressure developed by the gas molecules. The pressure exerted by the gas molecules is due to the gas molecules striking the sides of container. So whenever gas molecules move, they always strikes the walls of container. Whenever these gas molecules strike the walls of the container, then the pressure is developed. So pressure is not due to the molecular collisions but due to the molecules colliding or striking the walls of container. Collision between the gas molecules is not responsible for pressure, but the molecules striking the walls of container is responsible for the pressure exerted by the gas. So I repeat again, whenever gas molecules move, they always moves in random motion. During this random motion, there are thousands and thousands of collisions, intermolecular collisions between the gas molecules. So these collisions will not lead to the pressure exerted by the gas. The pressure exerted by the gas is due to the molecules striking the sides of container. So whenever molecule strikes the sides of container, pressure is developed. So pressure is due to the molecule striking the sides of container. Next, now these gas molecules, the motion of gas molecules to the motion of gas molecules, classical theory, that is Newton's laws of gravity, specifically second laws of motion, is applicable. Laws of classical mechanics that is specially Newton's second law is applicable to the motion of gas molecules. Next postulate regarding this kinetic theory of gas is, now we have these gas molecules which are identified by tiny spherical particles having identical shape, size and mass. The volume occupied by the molecules of gas is approximately 0 in comparison to the total volume of the gas. Motion is static, smooth line, straight line. There is no force of attraction repulsion between the gas molecules. So when these gas molecules moves in straight line, the speed at any instant may be from very small value to very large value, but the average kinetic energy of the molecules depends only on the absolute temperature. This average kinetic energy does not depend on the mass of the molecule, but this depends only on the average temperature, that is absolute temperature. So average kinetic energy of gas molecules depends only on the absolute temperature. So when I use this term, the kinetic energy of the gas molecule is independent of the nature of gas, is independent of the mass of the gas, but this depends only on the absolute temperature. So therefore look at it. Average kinetic energy of the gas molecules is directly proportional to absolute temperature, or we say this average kinetic energy is equal to some constant K into T, but K is a constant of proportionality. So average kinetic energy of the molecules increases as the absolute temperature is increased, decreases as the absolute temperature is decreased. So these are the main postulates based on which we develop a theory which is known as kinetic theory of gas. Now specifically this kinetic theory of gas is applicable only for ideal gas, because this theory is developed mainly to explain the experimental gas laws that we have discussed. Now based on these postulates, we have developed a mathematical equation, the derivation of which is not required. The derivation will be discussed in detail in physics. Now we'll just use the final equation to explain the experimental gas laws. So considering this, the equation developed is known as kinetic theory of gas, kinetic gas equation. So the kinetic gas equation is PV is equals to 1 by 3 m n u square. Where P is the, let this be equation A. P stands for pressure of the gas, V for volume of the gas, M mass of individual gas molecule, but this N is the number of molecules, U is the average speed of gas molecules. So these are the different terms. So pressure into volume is equal to 1 by third mass number of molecules into average speed square. This is one equal as kinetic gas equations. Now we'll modify this equation slightly by using this average kinetic energy condition. We have written this kinetic energy is equal to half m u square. So using this equation A can be modified as pressure into volume can be written as 2 by 3 half m u square into n. So look at this. This is average kinetic energy. So therefore this can be written as 2 by 3 into average kinetic energy into n, and therefore look at this, 2 by 3 average kinetic energy is kT, so n k t. So as well look at this, n is number of molecules of gas, k is a constant, t is the absolute temperature, and this k, which is known as r by n a, n naught. So r is gas constant, n naught is Avogadro number, this gas constant divided by Avogadro number, this is known as well as 1.38 into 10 to the power minus 23 joule per Kelvin. This is known as Boltzmann constant. Let this equation, that is PV, let this equation be B. So we have this is the main equation, this is the derived equation. So now we are going to use this equation P to explain experimental gas laws. So first look at this Boyle's law. Let's explain Boyle's law. Now Boyle's law says temperature and the number of gas molecules has to remain constant. For Boyle's law to be applicable, temperature as well as number of moles of gas. Number of moles of gas means number of molecules of the gas has to remain constant. So under this condition, now look at this equation B. T is a constant, N is a constant. So we have look at this, N is a constant, T is a constant, K itself is a constant. So therefore the right hand side of equation B is constant. Therefore from equation B, pressure into volume is equals to constant. So what is this is what equal as Boyle's law. Or we say pressure is inverse sum is equals to sum constant by volume, or we say pressure is inversely related to 1 by V. This is what we call as Boyle's law. So we can explain from this equation the applicability of the Boyle's law. Now coming to Charles' law. Charles' law says pressure and N has to remain constant. So pressure and N being constant. So we have from this equation B, from equation B, we have V is equals to 2 by 3 Nk by P into T. So pressure is a constant, N constant, K constant. So this term in the bracket comes out to be constant. So therefore this can be written as volume is equals to some constant K, or we say constant, into temperature, or we can say volume is directly proportional to absolute temperature provided pressure and number of moles of gas remaining constant. Then we have Gail Sachs law. So Gail Sachs law says volume and number of molecules remaining constant. So volume and number of moles remaining constant. So therefore from this equation B, we have pressure can be written as 2 by 3 N K by V into T. So this term inside the bracket is a constant. So we say pressure is equals to some constant into T, or we say pressure is directly proportional to absolute temperature provided volume and the number of moles of gas remaining constant. Then we have Avogadro's law. So Avogadro's law says pressure and temperature remaining constant. So pressure and temperature remaining constant. From this equation B, we have from this equation B, V is equals to 2 by 3 K T by P into N. So this term inside the bracket comes out to be constant. So this can be written as V is equals to some constant into N, or we say V is directly proportional to number of molecules of gas provided pressure and temperature remaining constant. So this is all the four gas laws that can be easily derived from this. Apart from this, we are going to derive some important derivation from this kinetic theory of gas. So next is average kinetic energy of gas molecules. We have to define this average kinetic energy of gas molecules. Now we have this equation A, PV is equals to 1 by 3 m n u square. Now this was written as 2 by 3 n into half m u square. So this was defined as the average kinetic energy. So therefore PV is equals to 2 by 3 n into average kinetic energy. So therefore average kinetic energy of gas molecules is equals to 3 by 2 n. Is equals to 3 by 2 pressure into volume divided by n. So this is average kinetic energy of gas molecules. Now we are dealing with ideal gas. So therefore for 1 mole of an ideal gas, 1 mole of an ideal gas, so 1 mole, so for 1 mole of ideal gas, this n is equals to Avogadro number, and for 1 mole of ideal gas PV is equals to RT. So therefore from this equation we have KE, average kinetic energy of gas molecule, this is equals to 3 by 2 PV is equals to RT divided by Avogadro number. So R upon N naught, this was defined as Boltzmann constant. So this is 3 by 2 times K T, where K is R naught R by Avogadro number, that is Boltzmann constant. So the average kinetic energy of gas molecule is equals to 3 by 2 kT. This depends only on absolute temperature. Then we have total kinetic energy. Total kinetic energy of gas molecule. This is average kinetic energy. Now the total kinetic energy is average kinetic energy multiplied by number of molecules. So this total kinetic energy total is equals to number of molecules into average kinetic energy. So this equals to N, that is 3 by 2 N K T. So again we are dealing with ideal gas. So therefore look at this. For 1 mole of an ideal gas, N is equals to Avogadro number. Therefore N, so therefore total kinetic energy is equals to 3 by 2 Avogadro number K into T. So Avogadro number times K is defined as R. So 3 by 2 RT. So this is the total kinetic energy of 1 mole of ideal gas. For n moles of an ideal gas, total kinetic energy, this is equals to 3 by 2 nRT, where n is the number of moles of ideal gas. So this is the total kinetic energy of gas molecule. This is the average kinetic energy of gas molecules. Now again, after this we are going to discuss the molecular speeds possessed by the gas molecules. Molecular speeds. Now these molecular speeds, this is of three different types. Root mean square speed, which is known as RMS. Then we have average speed. Then we have most probable speed. Most probable speed, average speed, and root mean square speed. Now first let's define what is root mean square speed. Root mean square speed, URMS, where U stands for speed, RMS root means square speed. So therefore look at this, root mean square speed. So this is U square of speed, then we have root mean square speed, URMS. Yes. So square, average, root. So root mean for average, square means we have to take the average of the squares of the speed followed by its root. So these can be written as U1 square, U2 square, U3 square plus UN square. These are the squares of the speeds of molecules 1, 2 through up to n divided by n, that is the average, then we have to take root. Now for ideal gas, this URMS root mean square speed, this is equals to 3 RT by M, where 3 is a constant, R is a gas constant, T is the absolute temperature, M is mass, molecular mass of the gas. Now in standard units, it is RMS speed, meter per second. So if this is to be measured in meter per second, then this temperature should be in Kelvin, means mass must be in terms of kilogram unit. So this is what you call as root mean square speed for ideal gas. Then we have another speed, that is average speed. So average speed, UAVG, average speed of ideal gas is U1, U2, U3, that is U, and that is simply the average of speeds. So for ideal gas, this speed UAVG, this is equals to 8 RT by pi M under root. That is the average speed. Now then we are left with most probable speed. Most probable speed. mp. Now this most probable speed is the speed possessed by maximum fraction of gas molecules. This is the speed possessed by the maximum fraction of gas molecules. This is defined as most probable speed. So therefore this, for ideal gas, this most probable speed is equals to 2RT by m. So if you look at this, we have three different speeds defined for these gas molecules: root mean square speed, average speed, and the most probable speed. When we compare these values, this root mean square speed is always greater than average speed, which is always greater than most probable speed. So the maximum largest speed is root mean square speed, and the smallest speed is, smallest value of the molecular speed is most probable speed. Now this speed distribution is defined by law which is known as Boltzmann Maxwell distribution of molecular speeds. Maxwell Boltzmann distribution of molecular speeds. So for this we have to make a graph. That is, this is fraction of gas molecules, that is speed of gas molecules. So this distribution of speed is found to have this type of graph. This particular point, this is the speed possessed by maximum fraction. This speed corresponding to this point. So this speed is most probable speed. That is speed possessed by maximum fraction of gas molecules. Now then, this particular speed at this point and speed at this point. So this particular point is average speed and this point is root mean square speed. So this is at a particular temperature T1, but if temperature is increased, then this speed becomes more broader. So this is temperature T2, and if you increase the temperature further, then this becomes peak. So this is temperature 3. So temperature T1 is less than T2, which is less than T3. That means as the temperature increases, the sharpness of peak decreases or broadness of the peak increases. So this distribution of speed is what we call as Maxwell distribution of molecular speeds. So these are some of the important derivations that we have defined from kinetic theory of gas. Now based on this, let me just explain it or do some numerical problems. So look at this question. The average speed at T1K and the most probable speed at T2K of carbon dioxide is 9 into 10 to the power 4 meter per second. Find the value of T1 and T2. So first we have average speed, that is 8 RT by m, and most probable speed, that is 2 RT by m. So this is T1, this is as T2. So these value is equals to 9 into 10 to the power 4. These value is equals to again 9 into 10 to the power 4. Now we have to find the value of T1 and T2. So therefore look at this. Squaring these two we get 8 RT1 by pi m is equals to 81 into 10 to the power 8. So from this we can find the value of T1. So therefore T1 is equals to 81 into 10 to the power 8 into pi m divided by 8 r. So we know the value of pi 3.14 m. Molecular mass of the gas is 44 gram. So this is we converted into kilograms. So 44 into 10 power minus 3 kilogram. So we say this is. So we know the values of this. We can easily find the value of T1. Similarly, look at this. Squaring this we get 2RT2 divided by m, which is equals to into 10 to the power 8. So therefore T2 is equals to 81 into 10 to the power 8 into molecular mass divided by 2r. So by using the value of this m and r, we can easily define the values of T1 and T2. This is one of the equations. How to use this most probable speed and average speed to find the values of temperature, provided the values are given to you. Now look at the second question. The average velocity of gas molecule is 400 meter per second. Calculate its root mean square speed at the same temperature. So question says the average velocity. So UAVZ, average velocity, that is 8 RT by pi m. So this value is equals to 400 meter per second. Then question says what is URMS, that is 3 RT by m. So we have to find the values of m. Temperature, question says temperature remaining the same. We have to find the values of m. Once we know the values of m, we can easily define what is this root mean square speed. So look at this. To define this, we need to have the values of this RT by m. So therefore look at this. Squaring this, we get 8 RT by pi m is equals to 400 square. So therefore look at this. RT by m is equals to 400 square into pi divided by 8. So we have the values of RT by m from this average speed. Once we the values of RT by m, we can use this value here. So using the value of RT by m here, we get, therefore URMS is 3 by 3. RT by m is 400 square into pi divided by 8. So 400 square. So we have 400 under root 3 pi by 8. So this is the root mean square speed. We have to find this value, that is meter per second. So that means for this we need to know the values of this equation, that is average speed, root mean square speed, and this most probable speed. So these are some of the examples in which we can use this. So one thing that we have to keep in mind is the most important part of this kinetic theory gas is the postulates. So the many times questions are asked from these postulates. Okay. So we have to be very careful about the postulate. We should know the different postulate that is used for this derivation of kinetic theory of gas. Okay.